Hi, I'm Matt Foster, an engineering physics student at The Ohio State University.
Hi, my name is Alex Brothers.
Hi, I'm Jeff Hensal, a computer engineering student here at Ohio State.
What IFEC is it's an annual competition for undergraduate students focusing on power electronics.
So the topic for the 2018 International Future Energy Challenge was a 1 kilowatt high power density, high efficiency, bi-directional, isolated DC-DC converter, or in layman's terms, bi-directional battery charger. So this is used for renewable resources such as solar and wind, where the resources are very intermittent.
So our team got to design from the ground up 2 prototypes. This included the design, as well as the debugging and the testing of these. We got to progress through 2 rounds of eliminations as the only American team in the final 10 for the final competition, which was held in Beijing, China. We were very happy with how we did. We got our final prototype to achieve a power density of 1.63 watts per centimeter cubed, as well as achieved a 91.5% efficiency at the full power rating. Based on our performance at the competition, we were very proud to be granted with the Outstanding Presentation Award.
I worked on the magnetics design for the converter. This entailed working on a planar transformer and inductor, which did the power transfer in our converter.
And I worked on the hardware design for this project, including the 2 prototypes.
And I worked on the microcontroller programming for the circuit controls and the user interface.
This is our test setup. Here is a battery simulator, and we use this as our battery load or supply, 40 to 48 volts DC. This is our high voltage DC bus, which is 400 volts DC. This is an oscilloscope for measuring signals and waveforms on our converter. This is the power analyzer. This measures the input and outputs of our converter to measure the input and output power and thus calculate the efficiency of the converter. And lastly, this is our converter and battery bidirectional charger. We use PI control and a startup method to achieve 0 to whatever the load current is going to be. So what we'll see on the scope is the DC battery charging current will go from 0 and slowly rise to, in this case, about 12.5 amps. And here we will see the phase shift current, which is the power transfer current going through the planar magnetic. This will also rise from a small AC signal to a larger one.
So not only did we get to learn a lot from doing graduate level work, we also got to travel to exotic places such as Beijing, China, where the final competition was held. We were the only American team there, so it was very eye-opening and a great experience to see more of this world.
For me, this project was very influential in terms of my career. In fact, for our qualification round, we got to go to San Antonio, Texas to present our preliminary prototype and our testing results to try and make it into the final round. And while I was there, I made a contact with my actual next employer, which is very exciting. And this project definitely gave me a lot of experience in power electronics and made me realize that I really love doing this kind of design and testing work. And I'm very excited to hopefully dive into a career involved in power electronics, largely because of this project.
Just being in China and networking with and meeting so many people from all around the world. There was Chinese professors, Japanese professors, some from Australia and the UK. It was really an enlightening experience.
We heard about this competition from our professor, Dr. Wang. He saw we were all interested in power electronics and really gave us the opportunity to have this experience.
We'd really like to say thank you to all of our sponsors, including Texas Instruments, Saturn Electronics, GAN Systems, EPC, and Rome Semiconductor for their component and financial support throughout this project.